Okay, I guess I get the distinct honor of introducing Dr. Steve Kite. Steve has been here 37 and a half years and started in James Madison, went to Maine, and then he did Wisconsin. Go Badgers.
Go Becky.
Go Badgers. Badger. Yeah, you can tell that story sometime. But Steve loves landslides and rock slides, things like that, floods. And he came into my office on, I believe it was Wednesday, this week. It was this week, Wednesday, not important day. And he was all covered in mud because he was all over the hillside out there. And he had a great big smile on his face. So I'll let Steve, and I'm not going to repeat his title. You can read it.
Let me go over the title.
Well, I figured you'd be a happy talk.
Yeah, right. It's a long title, and actually I've modified a little bit from what was in the flyer. How many folks in the back? How's the sound? Is this too much? Loud enough?
You know, you're fine.
Thumbs went up. I thought maybe they got thought maybe be louder. All right, we're gonna try to stay closer to the mic. I am going to stay here and use my cursor. I have an extra big cursor just so I can see it. But the title of my talk, Countless Landslides. I made this title up Monday morning, and not knowing that what I plan to talk about is going to be superseded by about the first third of my talk today, which is a particular landslide, which I counted as one, that you all may be very familiar with. Unstable foundations may be a better word for wobbly. Depraved roads. Some people are kind of objective to that. I don't mean anything bad to hurt my highways or anybody like that. But you know we have highly problematic roads here in this town. And the wacky street networks. I am probably not going to talk as much as I originally planned on about the foundations and the wacky street networks. And I will talk a bit about those, maybe a slide or two. But then following that, it's sort of a why. How ice-age stream pirates captured the St. Lawrence drainage system and created the Mons complicated topography. The topography we have today is not the topography you would have seen had you gone back in time 2 million years and looked at this landscape. You might not even recognize the major river systems. And if you go back 13, 14, 15 million years, you might not even see much mountains in this part of the world. Well, the landscape has changed quite a bit. But at any rate, I have, what I was going to do is not necessarily what I all along planned to do. So maybe a little bit of a disjointed talk just because I've interjected so many things here at the last minute. So I want to lead off talking about the 25-ton elephant in the room. And that is the rock fall that happened just the other day. You've seen these images if you've been on a lot of the media. Morgantown Police Department posted these, the PRT card. I will point out something to you that the PRT card has an impact feature on it. So you hear both ways, whether the car ran into the rock or the rock ran into the car. It looks like that the rock actually came down, jumped over the Jersey barrier that's there and hit the PRT car. There's yellow paint on that rock. If it hit it like you see it right now, there'd be no yellow paint on it.
One of the damage that was the fire department cutting the window out of the, that's what all the damage to the car itself was, the fire department cutting the people out of it.
This right here, according to the PRT folks, told me that that's where it hit. But you're right. Yeah, most of the big gaping holes, jaws of life, I guess, cutting through. Yeah, again, if you had comments, this is wide open because I'm talking about something I think I'm trying to get all myself wrapped around it. Anyway, there's the unfortunate automobile. I think that ran into a boulder that had already come down. But if somebody drops a boulder in front of you and you're doing 45 miles an hour, you have not much time to react. Every one of us would have the same issue.
This morning, I was told that there was dash cam footage from inside the car that showed the boulder more or less fell on top of it.
Really? Okay. Well, I'm a little dubious because of the crumpling of the hood, the way the hood is crumpled back. So if it's immediate, simultaneous, it doesn't really matter. If you look at the videos on YouTube, it would not matter. It's certainly it was bad timing. Half a second later, 2 seconds earlier, 5 seconds later, we've got a different story. So it's a very unfortunate sort of thing. And then here is I'll break this out to you. I'll come back to this in just a little bit. This little area where there's some trees. Anyway, I first found out about it when Susan's girlfriend sent me a text message that says, oh, this is going on in Lake Block. So then Shannon Maynard, who works on the landslide project with me here in the tech center, she sent me this image and I said, wow, I gotta go see. Now, I was at home and my wife keeps saying, Steve, be safe. And so she also pointed out at this time of day, which is like 4:15, 4:30, we were never going to be able to get there with the traffic, especially with the road being closed. So I decided next best thing, I would drive over to Westover by way of the I-68 and then drive down Hill Street on the other side of the river. So this picture here was taken in pretty heavy rain. And I noticed there was a lot of motion going on there, a lot of flashy lights. So I said, well, I bet I know what happened. I can tell anything from half a mile away. And that this landslide right here was activated, and that's what put the rock back in place. And I thought that's kind of funny because the big rock's up on top of that scar right there. So I couldn't quite figure out where that rock was coming from, but of course I knew what was going on. And then actually I looked at some of the photos and said, well, maybe we better go look. So the next morning, Matt Bell and Rachel Chidlow, for the landslide team, went out and looked at it. We found a place where, notice here there's brand new fencing where the replacement fencing didn't take place of what went through. Obviously, this is not a rockfall retention fence. Right? So it's a security fence for a lot of things, but it'll catch some small stuff. But it's clearly wasn't sufficient to stop that rock. And the size of that rock, it's not surprising. It didn't. But amazingly to me, the unusual thing here, it's not so much that the rock made it to the Jersey barrier, but it went over the Jersey barrier. And I think that's important. Everybody's calling this a rock slide. If it was a slide, it would have slid up against the barrier. It was bounding. It was a rock fall that was bouncing. And that's why I kind of object, and I was really glad to see in the sex issue, the most recent DA, that the reporter on that did a great job in calling it a rock fall. And I think they did a pretty good job of that. So had it been a rock fall, in ways to a PRT is a much greater danger than a slide. Slides are normal out there, really common, problematic for the road. The rock fall is more of a problem for PRT. Here's Matt standing next to the divot. It seems to be partly filled in, that the rock made right as it hit the edge of the road, broke part of the culvert. I think it's probably where it shattered. Right? And then the other pieces continued on across the road. So here's the biggest piece, smaller piece in the third lane. And here's Matt for scale. And I'll draw your attention to the pathway. That's where the rock came down. Agreed? Yeah. And you can see if you follow it up, there are all these broken trees on the way down. I talked to people, and there's an auto party over across the river. They said they first thought it was tree falls because they heard the trees breaking, and then they heard a couple of thumps where the rock hit the road. So at any rate, there's the pathway, and we were able that later on that day, about 9 o'clock or so, we were able to get on top of the cliff in the forest above where we could see the trail beginning. Matt and Rachel and I agree that we could get down to the front of the cliff. Thought maybe that would not be a great idea at this particular moment. And also thought, I'm not sure we'll be able to get back over the cliff in the wet weather that we had. So I'd like to go back at a drier time just to kind of look at that. Yes.
Could this event have been predicted, or is it just spontaneous?
Can I come back to that?
Yes.
Utilizing time, yes, it's predicted. Alrighty. Let me come back. Okay. Yeah. I mean, I think that's 64,000. $15 million. All right. So here's the pathway. The parking lot for the greenhouse is in here. A couple, 3 parking spots over. I think is right above where that failure occurred. Came down here, broke up. Big piece, smaller piece a little further, and then the one piece that went up and over. Yeah, go ahead and have a seat up front. Please, you can see more. Cross legs. I used to do that back in my day. All right, so the slope of all the roads, about a 80% slope, 38 degrees for geologists in here, a 1.3 to 1 slope. Really pretty darn steep, tough to walk, barely walkable up. The cliff face itself, that would be a little trouble. Rock dropped up close to 50 meters, 150 feet, where it was to where it wound up. Total run out laterally, about 100 meters or so. And then the cumulative weight of the rock, adding the pieces together, the three biggest pieces, will be somewhere in the neighborhood of 25 to 35 tons. A lot of rock. Heavy rock. Assuming quartz, sandstone, typical weather rock density. Now, okay, so where did it come from? What's the situation that's coming from? This picture I took over 20 years ago of the big landslide scar. And you can see the big problem that's going on in that outcrop or that road cut up there is that there is a sandstone that's fairly massive called the Connellsville type localities up in Pennsylvania. And that is cantilevered because the underlying rock is weathering away piece by piece by piece, winter after winter after winter after winter. And as the underlying shale siltstone bedrock weathers away, that upper hard sandstone bed becomes more and more precariously cantilevered, and eventually enough rock falls out beneath it, and boom, down the rock will come. Smaller rocks do this quite often. Sometimes rocks come from other places on the old scars, but the biggest problem out there for rockfall is right there. So let me get back to the other picture in just a minute. On the right side. This is the path just off screen where that rock fell. If you'd asked me, where's the rock going to fall from? I would not have said coming from in the woods. I would have said somewhere on that bare rock slope that's up there. So the specific place, I would not have predicted. In fact, your question. But knowing that road the way I do, being here 36.5 years, 37.5 years, I know that this is not the first time. And here I have an image, a really crummy image I took of March 1966, 1996, and a rock had come down from there. You can actually see, I think, where it came from right there. It fell down, smushed the Jersey barrier. It didn't run quite as far out into the road, but still. Somebody said they knew of a person who had a car that was damaged by this fall. More recently, Mitzi Shady, I knew you know Mitzi, PhD student, just recently. She had an 8-inch block fall off that and hit her car last February. So it's a very active slope. Mostly small pieces. This was not small. All right, this is the biggest one in my tenure here. This made it on the front page of USA Today. They called it a 100-ton boulder. I measured it carefully, figured the density out, and said, no, it's only a 70-ton. But you can see that's a bit problematic. And draw your attention over here that there was a boulder that made it up against the Jersey barrier near the PRT in that time as well. So this again is more of a rock fall than a slide, because it's coming from way up on top of it. Here's an even older slide right here. This is a picture Ken Martis took in the spring after the big one in 1983. And there's a picture of Ken, and then beside Ken is Dr. Alan Donaldson, the chair, the guy who hired me here, who I'm dearly indebted to. And Alan had a handout that Joe Lebo let me copy. And Alan showed an area of exactly what's going on with the geology here. You got this resistant Connellsville, shale weathers out from underneath of it, and then periodically, boom, down comes a block and fails. And you could try to just fix things right here, but if you don't keep the shale from going back, you're going to have a problem. So it's the whole outcrop, the whole exposure that presents an issue here. Well, I'll continue on with this vein because we get a little deeper into it. Just context, Alan, the diagram show you the engineering campus and all. I won't belabor that, but I thought that was kind of interesting how he took kids in the SED strat class and talked about it. I took kids in the Jim Wolf class and talked about it as well. Here's the big one. And it's my understanding secondhand, because I wasn't here then, I don't know. It's the nice thing about being the oldest person in the room. Maybe, I don't know, Greg, you might remember this. It's not your old, longer serving person. Yeah. But it's my understanding that before this 83 big slide, there really wasn't a lot of activity.
I was walking to work in those days, so I probably didn't come across it in a car. But yeah.
Yeah, it was really starting with this event that things became problematic. Now, some of you may be local, may know a little more than I, but Al said, it was funny how the road was built about 1960, more than that, but it wasn't until 20-some years later that the big slide occurred. So it takes some time for the geomorphic response to occur.
There are pictures that Vika Haas has found in the History Center that show active slides in 1890 and 1905
I'm not surprised.
as well.
I'm not surprised.
Same exact spots.
Yeah, that is a very steep slope. And it was bold to put a road to the bottom of it. Divert for a minute and say something maybe I shouldn't, but I will. There are some roads around here that probably should be annulled. One of the last block or so of Forest Avenue, that's never going to be fixed. It's a road too far on the steep slope. And sometimes I wonder about River Road. Similar setting. So I think we have to kind of come to grips with that. Sometimes it makes sense short term, long term, we just can't afford to keep doing that. All right, the wonderful pictures here of this slide. This PRT worker, I guess, was there kind of sizing up the situation. It's still a telephoto, so he's not quite in as great a danger as it might seem, but still, I'm sure it was quite an adventuresome time. You can see his legs sticking out right here. He was not in harm's way, but I'm sure his heart is coming down. And then here they are a little later on here at the block. It almost made it up to the PRTs. I don't know if it was closed, PRT was closed that time. I think I've heard that it was briefly. And also a point, the DA had an article on that, and notice
He was here.
that was way back in the time when Gordon Key was president of the university. Come back to the geobroad thing maybe at the end. Right, and again, back to the issue that there have been historic slides going back a century or more. This was a very steep slope. And you notice here in 1925 on the topographic map, there's no road there. And Morgantown had kind of grown to that area right there, the Seneca/Sunnyside area, and it pretty much stopped there because there was no road. And there was a railroad, but that's at the bottom.
Yeah.
And they had priority because they got the good ground. And so when the road was built, they had to come up above the railroad right away and bring it up to the Evansville campus. So no road. And here's what the landscape looked like about 1960. They're building engineering building, the old ag sciences building, a few other things that you see up here. And apparently the road actually, I understand, dates to the 40s as a 2-lane road. In the 50s, they expanded to a 3-lane road. And then in 60, it went to a 4-lane road. And I think at that time, they widened things a lot. Because look how fresh this cut is through here. How much vegetation has been taken right to bedrock. Vegetation, soil, and everything back to bedrock. So I think herein lies kind of the beginnings of the real issues right here. This was a very bold road. And again, it made a lot of sense from pragmatic getting from downtown campus to the new Evansdale campus, which used to be the golf course. But here, superimposed off to the side, I put the track of that recent rockfall here. So I think it was coming from somewhere about right here on down up to the roadway today. Another picture of this Mon Boulevard back. This was actually the next year. You see what they did. They cut the slope way back, steep, no benching. And you can get a sense here, the nature of the rock that's here, it's shale, sandstone interbeds. This is a curious slope. It's a good slope for one who teaches geomorphology, teaches about landslides and rock. Anyway, so that's where I think things begin. All right, so what I want to focus here is, yes, there is an anthropogenic element. Most of all the slides you see around Morgantown, you can put your finger on it and say the trigger is anthropogenic. Somebody did something. So maybe with drainage. All righty. But on the other hand, there's a larger context that there's a reason why the Monongahela River was named what it is. The Algonquin word means what?
Falling banks.
Yeah, falling banks. So the Monongahela River is the river of falling banks. The a number of people who lived here recognized that this was a geomorphic hazard. And it remains so today. So, and Morgantown's not alone. This is a larger picture borrowed from some talk I gave at GSA. So somebody who I know Lee might have been there. But my apologies if it gets redundant for you. But some points I made then I don't make now. West Virginia is a landslide heaven, so to speak. 70% of the state is mapped by USGS, was mapped by USGS as being at high risk of landslides. Second place is Colorado with about 25%. So, Colorado's a lot of landslides, got more people. California has even more landslides, but they have way more people. So on a per capita basis, West Virginia is probably number one or maybe number two in terms of per capita landslide damage. I think actually it's part of our cycles of poverty and this flooding that we spend an inordinate amount of money to avoid landslide problems when we could have that money to do other things with, like build better roads, resurface existing. So much of the state is highly prone. Well, in response to the fact that it is a hazard, FEMA recognized landslides as the number 2 hazard in the state after flooding. That we embarked a little over a year and a half ago now on a landslide inventory and risk assessment. The risk assessment is kind of forward-looking. We've gotten good progress in the landslide inventory. Matt Bell, Matt here? Oh, hey, Matt.
Made it.
And then Shannon Maynard's done a lot of work on that as well. So other people in the tech center. So first thing we did was try to put together all the existing records of landslides, and we're actually very rich in terms of records of landslides. Most of the data was collected 30, 40, 50 years ago, but we still have a lot of data to work with. There is one problem: is it was done by a bunch of different people using different methods, and it's disparate data. And we're actually going to wind up trying to model the landslide risk based on our own data. But we start off with inventorying the existing data. And I don't want to go too far into this slide. I can get hung up on that at another show. Well, just text and move on. But we'll just talk a little bit about the existing landslide data and then move on to what we've been doing in the tech center, Matt and others have been doing the tech center. This is a tabulation of all the different kinds of landslide data. And the weighting is a little bit funky. It's a bit dependent upon choice of symbols. There's like 7 landslides near Kanawha City, an event that killed 3 kids sleeping in their bedroom. They're large symbols, so they look more important than the little tiny little symbols, which may represent landslides that are 10 times bigger. But a lot of the dark gray area you see here, really dense gray areas where the West Virginia Geologic and Economic Survey mapped 39 different maps in landslide prone areas with high population. And then with exception of the northeastern part of the state, the US Geological Survey came along at about the same time, a little later, and they mapped virtually the entire state. Both of these projects were done on air photos. And they could see a lot of things in the air photos as long as the landslide wasn't too old. I'm going to look a little bit here at some of the data points. We also have some highway data points. I think that most of the red ones here are Department of Highways data points. That's the Division of Highways, Department of Transportation. This is the USGS mapping of Quadrangle over near Parksburg, Rockport. These are the recent slides that are there. And then here on top of that are the older slides and the combination recent and older slides. This is 1/9 of USGS 15-minute quadrant. So it's 2.5 degrees by 2.5 degrees. There are, I counted, let's see, 44 olds, 12, we got about 147 landslides that USGS mapped. To get mapped by the USGS, it has to be big. So in this 1/9 of a quadrangle, and there are almost 400 quadrangles in the state. This one little sample we have enough big landslides to project out to be about 600,000 landslides in the state if this was representative state. No, it's not, but it's representative of a large part of the state. And so anyway, we do have a landslide. Well, it's a problem if you're a landowner, if you're a geomorphologist. All right, here are the West Virginia DOT, DOH mapping. And I thought, wow, we got a really great pattern here. They inventoried in the northern panhandle is landslide heaven. And I knew that was the case. It's a real problematic area up around Wheeling, especially along the Ohio River. But then I started looking a little more carefully at the pattern, said, you know, I think there should be more in here and so on and so forth. And then I came over to this map right here. These are the different districts of the Department of Highways, Division of Highways. And over half of the landslides that they inventoried was in one district's jurisdiction. So what it shows to me is one district really got involved in this, and the others were not so heavily involved. So I think there's a reality to that pattern, but nonetheless, I don't think that's the whole story.
The WDOH's research office is located in that district.
Okay. We have a true explanation now. Yeah. So anyway, it's neat data. It's also a little different data because it's more likely to include small landslides that would impact the roadway that might not be mappable in air photos of what we're doing. It's actually interesting to compare that data and see how many of those known landslides we didn't map using LiDAR. Getting off on that. So now we move on to what's being done here in the Tech Center. Shannon Maynard, Matt Bell back there. Shannon's not here today, but we developed a landslide protocol. We developed hill shades and slope shades where we have really high resolution digital elevation models. Good LiDAR is critical, right, Matt? Yeah, and we have good LiDAR coverage. It's a little bit outdated, but we have good LiDAR coverage for the eastern part of the state. So that's where we started. It's filling in the southern part of the state, so that's where we move next. It's beginning to fill in, I guess, as of Monday, this area around light detection and light, LI, detection and ranging, LIDAR, lowercase I. Okay, and we just got the counties here and Mercer County here. Mercer's got some neat stuff going on. So anyway, that's going to bias the next images that we see, which is, well, let me show you a few of the images. Now, these are from the eastern part of the state. We just haven't worked a lot with the older images. This is my favorite landslide. When I go see my mom, we go drive by this all the time near the Lost River. 500 meters by 500 meters. It probably all came down at once. You see these dimples right here? Those are individual blocks. They're too big to be called a boulder. One of them is 3 stories tall. And so, this would have been a bad day in Lost River. Here's the slope shade, show you particularly the biggest of the boulders. We also have debris flows. I knew about this 1949 little skinny stringy spaghetti thing. Did you see across that? I didn't realize it was on top of a monster. All right, you see this little thin debris flow. There's probably only like 10 or 20,000 cubic meters in the debris flow. All right, and then we look at this monster thing here, which is a kilometer long and 400 meters wide. So there's some really big landslides out there. And then rock cities or lateral spreads, like up at Cooper's Rock. This is the biggest one I know in the state, Beartown. If you haven't been there, go there. It's new faculty. Recommend you take a look at that. Anyway, I don't want to get too sidetracked. So there's our mapping a while ago, but here is our mapping as of 8:53, fresh from Matt's keyboard. And here the mapping we've done. You can see the holes that are created by the fact we don't have LiDAR up north. A couple of counties up north have their own LiDAR, so we tried to map in their area. But we're up to 33,000 some landslides that we mapped using LiDAR since last March, which I think is pretty good. And one interesting thing, going back to a map I showed earlier, the mapping, particularly in the southeastern part of the state, shows that there are a ton of landslides in areas that the USGS said was landslide, not landslide prone. So with that,
What are DEMs?
digital elevation models, right? They're basically digital landscapes to create from the LiDAR, light detection ranging data. And the vertical resolution on the DEMs that we're using, the Beth ones, 3 inches, 7.6 centimeters. Yeah. The horizontal distance, no, I don't want to make it into a LiDAR discussion, but it's really high resolution. Many of these landslides that we're detecting on the LiDAR, you can go there and you cannot see them because of the trees. The LiDAR is able to penetrate through the trees. If they process it properly, you can take the trees out and you will just see the bare earth underneath. And so I've been on these monster landslides, and even though I know they're there from the LiDAR, it's really hard. It might take you half a day to figure out where the landslide is. Matt can pick it up in 30 seconds and then move on to the next one. All right, so anyway, I changed my earlier statement. 70% of West Virginia is not extremely landslide prone. It's 75% of the state. So we got that wonderful claim to fame. That'd be the landslide state, right? All right, so far, talking about landslides, and leading up to it, we kind of said, well, humans are a big player in the landslides. This particular landslide is on the cover of this Geological Survey Environmental Geology Bulletin 15A, published in 1996. It's a cover girl of the landslide. It's a landslide that happened in 1996. If you're interested, I can send you a PDF if you need it. The courtesy of the Geological Survey. All right, but this is, well, you recognize the Colloquium, right? And this is near the natatorium. This was triggered when someone got the idea that rather than routing the water as they emptied the swimming pool to the natatorium, rather than routing it into the sewer systems, they poured it on the side of the hill. At the time, this was an active railroad. I have a dossier on the litigation. And I do not know the final solution because that was a sealed issue, but I know the numbers had 7 figures and in 1976 dollars as we were going into it. This landslide's still there, and when it rains, still pools water. So it's right above the rail trail now. Yeah, the railroad could go in and fix it. MRTC cannot then have the deep pockets of a railroad company. So, all right, people do funky things. I would say dumb things, but maybe only dumb to geomorphologists. There's also one issue, I think, in the state. There's no professional geologist registration. Engineers might be able to look at it, figure out a fix if they know the landslide is there. Geologists are a little better equipped identifying the landslide. Don't ask us to fix it. We'd never build anything. We have engineers, so we'd never get anywhere. But I think we might have a little better, as many other states do, having a PG look at some of these issues, requiring a PG to be involved in design of civil engineering structures. The other thing I found is mountaineers are always free, which means there is will. And I've done some consulting, often for engineers. Mine engineers are the most interesting. Because I mean, they're used to doing things in the mine. They can take on just about any challenge you throw at them. I remember consulting for this one fellow out near Treat Lake and said, this is the most problematic slope in all of Mon County. I would not put a townhouse here. No, we'll go on. All right, part of the problem is the geology, underlying bedrock geology. And I don't want to go into stratigraphy of the whole state, no time for that. But for us here in the Mon County, 95% of the rocks near the surface or at the surface is in this interval right here. And at the top of the Pennsylvania age rocks, they're all landslide prone to one degree or another. The Allegheny maybe a little less, but certainly Hospital is rockfall prone. But the Conemaugh, Monongahela, and Dunkard had actors. A lot of swing swell clays. Get wet, they expand. Dry out, they shrink. Get wet, they expand. That process often pushes the rocks apart and causes a lot of rockfall or failure altogether. All right, and anyway, the bottom line is our bedrock geology is not, it's compatible to landslides. It's not necessarily good for engineering. Now, if you get to the geology that matters to some of us, which is less what's underneath the surface geology, but the quaternary geology, basically the soils geology. All right. Quickly, I've kind of summarized this map that almost nobody knows about. It's a 1 to 1,000,000 scale Blue Ridge 6 degree by 4 degree sheet. Right? It was compiled by a group, and Bob Bailey was one of the compilers of it. He's the second author on this map. And what you see are some terraces and some river deposits. Some white areas represent what was mapped as mines or mine fill areas. I think maybe a little bit overly ambitious there, but to give you an idea, there's a lot of mine waste here, mine material. But 90%, way over 90% of this landscape is either abundant landslide deposits, scattered landslide deposits, or some kind of colluvium. What's colluvium? Landslide deposits with slope wash mixed in. So we look at this landscape, and 90% of this landscape or more is old landslide deposits. So if you're a civil environmental engineer or developer, that gets stacked against you, buddy, because if you go in and mess up old landslide deposits, what are you going to trigger? So anyway, it keeps me, or whoever will teach geomorphology hereafter, with a lot of field trip ammunition. I always promise students in geomorph, by March, we'll have some landslides to look at. Only 2 years out of 30-some days, I'm disappointed, or surprised. But anyway, why is the setting so precarious? Part of it is these Ice Age pirates. The Mon River used to drain north, past Pittsburgh. There was no Ohio River at that time. It kept going north past Youngstown, headed up to Lake Erie, took a right, joined the St. Lawrence River, went out past Quebec today. Right? Also, there was another river called the Taze River that probably did the same. Right? So we had an ancient drainage. All of North America's drainage has totally been changed by the Ice Age. You can imagine once there's a great mass ice sheet going down from the south, that's not that can't be done. The water can't flow over that ice sheet. So all of a sudden, it has the water running off the glacier has to find another route. So it has to find a route to the south. And so eventually, that causes the whole St. Lawrence to be rearranged. The response to that is creating incision of the river valleys as well as nick points. I'll come back to those in a minute. And then that incision, down cutting of the landscape, leads to slope instability, and it ain't over yet. It will probably continue for, I would guess, 1,000,000 or 2 years longer. All right, so here's the maximum extent of the St. Lawrence drainage. I mean, they were talking about the New River down North Carolina, probably drained out through St. Lawrence. Old versions had it routed over to Illinois. Most people working on it nowadays have it going off into Lake Erie. And with the alternate divide right here. And then here is a river, the ancestral Monongahela, particularly downstream from Pittsburgh, it's often called the Pittsburgh River. So the Monongahela could actually be thought of as the pirated Pittsburgh River. And I promised Ice Age pirates. Hey, pitchers and catchers reported this week. All right, this is the old system over in the Taze Valley, western part of the state into Ohio and Kentucky. It's really well known. Taze is a little depot here in the Taze Valley in West Virginia. There's Huntington there, Charleston over here. Here's a blow up of what that looks like in LiDAR, a digital elevation model. See the Gaul River goes here. There's the Taze Valley. Notice the size, almost exactly the same size. So it's clear that this river, even though it's a good 150 feet higher on the landscape than the existing river, it flowed through that valley about the same flow it has now. All right, if thinking of the larger consequences, if the Taze was part of this, if it's not part of the St. Lawrence, just adding the Pittsburgh River would increase the size of the Ohio River drainage by 12%. If the Taze was part of the St. Lawrence drainage, then that would increase the Ohio by about 34%. By the way, where the two meet, Ohio is a much bigger river than the Mississippi. So we're talking about the major drainage in the eastern United States, or most of the United States. Now, at the spot where the stream piracy occurred, where the water spilled over and cut a new path, on the backside of that drainage divide where it was topped over, those tributaries have their drainage area increased by 10,000% or more. You have a little creek, and all of a sudden it becomes the Ohio River. And that has great ramifications on the landscape. Also, in related to this, when the great white masses came down from the north, it blocked that drainage in the glacial lakes. Lake Kite is well known, a little less so is Lake Monongahela, which both I.C. White and Samuel B. Brown, yes, Samuel Brown. These are the first two chairs of geology at WVU. And they studied this issue, as did Al Donaldson later on, and Bob Bailey. So here's Lake Monongahela, and here's some of the Lake Mon sediments. I brought a sample with me. It was the beginnings of the pottery industry in the Morgantown area, which eventually I think morphed into the glass industry. So this particular pottery here is really nice for firing. And so anyway, we got these glacial lake sediments at a high elevation. They make for really bad foundations. Anybody here live in Suncrest? Have any problems with foundations?
No longer.
No longer.
But we did.
Yeah. All right. We're talking. That keeps you in a lot of work, Mr. Sexton, right? Yeah.
40 years.
20 years worth of work. Yeah. Yeah. So shrink swell clays, you can imagine, well, a lot of basements just kind of do funky things. Well, it's not good. Let's put that way. It's not compatible. We've had 3 friends who've experienced problems in Suncrest, the shrink swell clays. So unstable foundations. How long ago back in time? Well, this may be kind of an academic issue. There was one publication by the West Virginia Survey suggested it was the last glacial episode. It doesn't make sense with everything else in the radiocarbonates elsewhere. I think they wound up with dating beaver pond deposits on top of old lake sediments. Wisconsin, late Pleistocene beaver pond on top of lake sediments. Nonetheless, almost everybody agrees it's back there in time. How far back in time looks more impressive if you actually scale it on a linear thing like this, the Ice Age cycle. So it may go back as much as 800, 900,000 years ago. Some of the Lake Mon sediments are reversed. So to be reversed, you have to go back to the Buddhist Matayama reversal, back to the Matayama. And so over 788,000 roughly years old. And there's a debate between Leverett and I.C. White over whether it was 1 lake or 2. Howell's Lake. Leverett thought that it was outwash from the glaciers that dammed the lake. White thought it was the ice itself. Probably both are right at different times. This is a classic reconstruction of Mark Swift working on master's thesis in geography. He's put this together, classic reconstruction. All you have to do is to, here's the Pittsburgh River, Steubenville River, the other wing. These actually flowed north, opposite direction of the Ohio. And here are the drainage divides between them. Come back to those in a minute. But all you need to do is pull the glacier down a little further and you block 2 different bodies of water. And so I think that's probably what happened. And we just don't, the ice age is so far back, we don't have a good map, good deposits to map that ice margin. Well, I don't want to get too far off on that. Here's a more recent map. The drainage divide up here, one called Midland, which was where the Monongahela broke over and flowed this way, joining up with Steubenville being reversed. And then down here is where the Steubenville Mon system reversed and flowed into what's now the Ohio and into the Taste. So at any rate, these drainage divides are important. It's done by Pennsylvania Survey, but it ultimately comes from drafting that was done over in Whitehall by the West Virginia Survey. This map right here, I have the original Mylar. We traced the 1,100-foot contour off of topo maps. It's one of my prized possessions. I don't know what I'm going to do with when you throw me out my lab. Here's the drainage divide. What were drainage divides? And what you see, there's high ground up here and high ground up here. And if you follow along the topography over here around Steubenville, you can kind of connect the dots up high, and all of a sudden, there's the Ohio River Canyon. It's 500, almost 500 feet deep. And maybe not all of that, but a big part of that, I think, has been carved by the new drainage that's poured over there. Right, here's an image of what that looks on LiDAR. There's a little room for a floodplain, but maybe not for Ohio River. There's a lot of glacial outwash. It may have been valley wall to valley wall. May have been big ice dam lake flood. And then here is the drainage divide on the Ohio River now, represented where the Steubenville and Pittsburgh rivers are separated. And that's only about 450 feet of relief, and that canyon right there. Again, this site over here particularly probably was a tiny little tributary until one day the water tops over and things change very dramatically. I don't want to spend a lot of time with this, but basically, the main point here is that the Steubenville River has a gradient on it. The high level terraces are backward. They flow north. They show sloping to the north. So that's evidence that the Steubenville was headed into the whole Pittsburgh River system. But we have these terraces all over. I don't want to spend too much time on this detail here, but it's a complicated story. I can't wait till I get all the LiDAR in and spend the next 5, 10, 15, 30 years on trying to reproduce this map right here. Here's one of the best terraces I've seen. This is on the Yakagani, which also flows into the Mon. It's just a beautiful terrace, 40 meters above where the Yakagani River is today. So it's a great example from the old area. But we don't have to go to the Yakagani. We can go about 50 yards that way. And we have a terrace that has terrace gravels on it that were excavated back in 2.5 years ago. You might see some of them on the entry as you come in from Life Sciences building. And those are deposited basically right there. So that's where the Mon River was before the big incision. And you can actually trace it at about the same level from here all the way to Pittsburgh and upstream of this past Fairmont. So we have about 48 meters, 59 feet of incision down to where the Mon River was before they put the locking dam system. So think about that. You got a river and it cuts down. All the tributaries have to cut down. All the slopes adjacent to the river or to the tributaries are steepened. This is why we're the landslide state in no small part. Now, bad geology, but also this late event. And to prove this, Mark Swift is working on looking at stream profiles. And this is what he's finding. I'll show this profile twice. If normally a stream comes out and it's ever more gentle in the downstream direction. Tributaries to the Ohio and the Mon don't do that. Almost invariably, they come down, they begin to flatten out, and then they get steeper. You follow roads that go along that. Driving, like go up I-79. As you're going to the Ohio River, the trucks all of a sudden are limited to a 45-mile-an-hour speed limit right before they get to the Ohio River because the landscape is so out of equilibrium, it's so steep going down the river. So this is happening on the tributaries here. This is Mingo Creek. And if you actually projected what you would expect the profile to be, it comes out right where those terraces are. So the upper part of the watershed is still aligned with where the river used to be. And what's happening in here is the tributaries are trying to recover from this, to try to come back to equilibrium. And here's a map showing where that particular stream, Mingo Creek, is. Here's the area of what we call a Nick zone, where it's steeper downstream than it is upstream for long lengths. So this is Mingo Creek. This is another one, Muddy Creek, a little closer here, and then Whiteley Creek. And this seems across all the different geologies that we have in this part of the world. So it's not just like a bedrock unit holding things up. It's across the different geologies here. So nonetheless, wacky road network. All right, if all the streams are cutting down, all the tributaries of those streams are cutting down, what would it be like to have a Wisconsin street grid on it? You know, with all the rectangles. The problem is, if you go from here to First Ward, used to be called South Morgantown, you got Deckers Creek. you go from here to Sunnyside, you got Falling Run. Anytime you cross a stream, you've got to put a bridge, a substantial bridge. Also, the topography tends to change. And so what we see, and this is an amazing map here, look how tiny Morgantown was in 1902. Now, the population in 2000 did not include Seneca, which is what we call Sunnyside now, didn't include a few other neighborhoods like Greenmont. But Morgantown exploded in population about that time. And you see, as it shifted, it went from a kind of a simple pattern that worked for downtown Morgantown. We did have a different pattern at Seneca for the glassworks. But you see, almost none of this lines up. If you take Route 7 from the Interstate 68 and follow it to I-79, it has 14 different road names. And very often it's right angle bend, turn here, wishback turn, all this sort of stuff. And part of it is just simply it's topography. You can't superimpose a logical grid on an irregular topography. So that's part of why our neighborhoods, our streets are kind of wacky. All right, well, I know I'm running close to the, well, I know. What are you gonna do, fire me, Tim? This is back to the Ohio River. I want to point out something here. Here's one of the Ohio River, I think it's Fish Creek. It's incised, trying to adjust to the Ohio River cutting down a bunch of old abandoned meanders here and there across the landscape. It's really a dynamic landscape. But look, all along the Ohio, all along Fishing Creek, I'll blow these up in a minute. You see, there's a preponderance of landslides in that position. There's landslides all over the landscape, but there's a preponderance of landslides near the rivers. Here's the Ohio River. This is the USGS map slides. Alrighty. So yeah, obviously there's something out of equilibrium along the Ohio River. And then here, that Fish Creek, not quite as dense, but still a lot of landslides right along the recently incised, geologically recently incised Fish Creek Valley. So I've already told you that about the landslide incidents, per capita damage. And what I want to try to do here, getting ready to wrap up, is to link this pattern from this map to this pattern right here. Because what you see is part of this high landslide prone area represents the old Pittsburgh and Steubenville drainage. Much of this high landslide prone area represents old Tays drainage. And both of these total reroutes, recently incised, create an equilibrium that's propagating its way upstream on the tributaries and causing all the adjacent slopes to be steeper than would have been the case 2 million years ago. I couldn't decide which of the landslides that have come down since our rockfall in West Virginia to show that, oh, it could be a lot worse, buddies. Your wave since old Route 52, I guess, has been rerouted, maybe not as important as would have been 15, 20 years ago. But that's happened, I think it was Tuesday night. Yeah. No, I guess that would have been Wednesday night. Wednesday night. It was in yesterday's paper. I found out. Is that? So I guess with this image, if it's countering our blessings, I will throw the floor open for any comments or questions that you folks might have. And particularly, I really appreciate the wonderful turnout. Jonathan, do you remember the day that big landslide occurred on the 21st of January, 1983? I knew he wouldn't.
I do remember it being published in the paper though. On the 24th, that was a good day.
The 24th is a good day. Yeah. What happened then, John?
Okay. Well,
New additions to the world, I guess.
Yeah. My son was born 2 days before.
Well, let's give him a big round of applause here.
Questions on the floor and
We are also going down to Morgantown Brewing Company, the near one, not Mountain Brewing Company, the one that's like 3 or 4 blocks away. We'll convene there. The brew pub. Thank you. We'll convene about 4 o'clock. We tried to get reservations, but there's no reservations on Valentine's Day, so we'll be elbowing our way in. But please join if you can.
Oh, the most important thing. Any questions that you want to ask? I know some people may need to leave, so feel free. But
Thank you.
Question or comment from the floor?
Yeah.
So Steve, you touched on shrink swell cycles related to moisture. You touched on freeze thaw cycles related to temperature. Both are increasing in variability in the precipitation and air temperature. And given the massive amount of rain we've had, which is continue to project into the future, what is your prediction for West Virginia over this 21st century related to changes in landslide, rock fall hazards?
I don't know if everybody heard Nick's question, but just kind of summing up. What about climate change? Yes. And I have kind of a typical response. We've had this discussion about way. We have a problem. We've always had a problem. It's going to get worse. And I mean, just this kind of winter where there's no snow, there's no sublimation of snow. Everything turns right to water, infiltrates. And so, it doesn't bode well well, it'll be exciting for the next geomorphologists because I think they'll have examples every year, except instead of occurring in March, they'll be occurring in January.
Yes. Can I just follow on to
Sure.
that and go even a step further? What do you think are the economic ramifications for the state? What are the costs currently, do you know? And like, could you imagine like an order of magnitude more, less than that, just like multiplicative?
Amy, I'd love to be able to answer the question, what are the economic ramifications for landslides in the state? But unfortunately, unlike flood damage, which is regular inventory, landslide damage has never been regulatory created. I mean, sometimes FEMA does, but it's got to be declared a national disaster. And many of these landslides are just one up. I mean, is that going to be declared a national disaster? No. And there's so many landslides that just got boom. And like this one here, that's part of a larger flooding unit area that might make it in, but it's not necessarily separated out from the flood damage. So first of all, I wish we had data. The only time we ever really collected landslide data was in the 1975 to 1983. A guy as a hobby at the SGS tried to do it. That's where I come up with the number one for capital landslide.
There's a state picture of the road is $6 million.
$6 million for
Just the road.
River Road. Yeah, I've talked to some former alums, who said, they're kind of tired of working in River Road. Okay. Well, I think that they're already enormous. Actually, we don't spend as much money, I don't think, fixing landslides as we do preventing landslides. And that's a cost that you might not be aware of. But how many retaining walls are being built here that you would not have to do in another part of the landscape? So, Roy, we have more business. To a technical word. And I wish I could give you reasonable numbers, but it stands to reason it'll be like flooding. It's going to be even more of a problem. Yes.
Is all the work that you all are doing in the GIS lab, is any of that automated, or is it all undergrads and graduate students like Matt just clicking?
Aaron Maxwell is here. Is he going? Aaron? Right. Where we are now, it's grad students are using criteria and mapping on LiDAR manually. Aaron is then turning into modeling landslide susceptibility using our maps. So if we are doing it right, he's actually getting closer. He analyzed, was it 43 different variables? Something like that, amazing number of variables in a paper that just came out from Mud Sensing a week ago. And if we're doing it right, we're going to get closer and closer to where one could maybe take the next step and automate it. People have tried this a lot. Problem is we have a lot of different kind of landslides that have different signatures. what I would use from the eastern part of the state where there are a lot of debris flows may not apply where there are a lot of lateral spreads, and that may not apply where slumps are dominant like where we are here. So I think we're moving in that direction. A lot of people try. It's usually people wind up getting maybe to work very locally.
Correlation is very good, like we are getting 94% like area under the curve. It's like random forest model is taking use.
Yeah, so that not me, that's the tech center in Aaron. The question, Josh.
Steep sloping of the tributaries was really fascinating to me. The whole thing was fascinating, like the mass reversal of rivers, carving out landscapes really quickly. I kept wondering if there was a way with the DEM LiDAR data to create kind of a visualization of that, where could I get back to 14 million years ago and watch what happened to the landscape?
Josh, there are some state geological surveys that have done a pretty good job with that. Wisconsin probably has the best. If you look at, they will show you the last 30,000 years of glaciation, which is not far back in time as us. But they've also put a lot of work into it. So unfortunately, we have a lot of gaps because we have a good record of a reasonably good record of the last glaciation, even though there's been 12, 15, 20,000 years since some erasure. The next glaciation back 140,000 years ago, we have a less good record because the subsequent glaciation erased a lot of it. And then a lot of landsliding and other things have erased some of the evidence in floods. Now we're going back maybe like 12 glaciations ago, 11 glaciations ago, when the ice first got far enough south to create drainage problems on this part. Upstate New York, those drainage problems happened much earlier, but in terms of the glacier, a friend of mine estimates the first glacier came into Pennsylvania about 900,000 years ago. And there have been multiple glaciations since. So unfortunately, we don't have the data to do it. Check.
Just a comment, the need for geologists to do this. I have a house out in Washington. Geologists wrote, don't build houses here. Also, landslide killed 30, 40 people. It's right. They're going to rebuilding again. And it was written up long ago. They shouldn't have built in the first place.
Yeah, any other, I have some questions I have to say.
I just know, when will they listen is what I'm going to say.
When we get organized.
I know.
Right, here, you touch the button.
Well, it's a button with me, it's an editorial comment, so.
About the same time as the professional geologist certification process began, in a year or so, maybe a year earlier, same time, professional engineering, PE certification began. Engineers are organized. Within a few years, every state in the union required PE certification for many, many projects. We're still at 31 states certified, some weaker, some better. 19 states, including West Virginia, Ohio, a lot of New England states do not have PG certification. If we were better organized, we would have more authority, but we like to wear flannel shirts and wear blue jeans and drink beer. We're not politically savvy. And I can explain to you how, I love engineers. I almost became one. I had different calculus. But they're a tight-knit fraternity with not a lot of sorority. But if we were as organized, if we protected our profession to the degree that engineers do, then we'd be much further along. Right. Yes.
I had two comments. The first one, as a native West Virginian, you're pretty much telling me we're screwed if we build in the valley or on the hillside. We're going to have something destroyed at one point or another.
Well, you can build on top of the hill, but then there's ice storms.
Well, or you can build on Target Mountain and the mines underneath collapse and then you're subsiding anyway. But, the other comment or other question I was going to ask is, once the assessment or risk assessment is completed holistically, what is your hope for the next step of that? Do you hope there's a regulatory facet to it, or do you think that essentially it's going to be something where people utilize it, not unlike the flood tool is being used now in the GIS Technical Center, but people start to kind of use it as an evaluation, maybe not quite to a regulatory role, but just at least evaluatory.
Yeah, I will work in this state where zone and plan are 4-letter words. Regulatory is probably not the way to go, but information is always useful. You know, I was a landowner, I'd love to know what the general problem is. We're not going to come up, we have no intention of coming up with a specific tool where you go out to your property and say, do I have a landslide problem? We're hoping to come up with this, hey, here, such and such county, this is the kind of landslide problem you have. This is where it's most likely to occur. So you can plan accordingly. Some of it, like a lot of the real big landslides over in the eastern part of the state, they're in the national forest. So they're real. They're great for showing on slides in a room, but they're not really, don't represent a risk to anything other than timber.
They're not a hazard, right?
Yeah, well,
They're not a
minimal
pathogenic
hazard. So, yeah, I think I would feel more comfortable with, information, making it available for people to figure out how best to use. But we're not, we're not gonna, we don't want to, but a number of efforts by state geological surveys to do detailed landslide mapping have been scuttled, including the West Virginia Geological and Economics mapping, survey mapping in the 1970s. Scuttled, cause and response. In North Carolina, we got a great mapping program in great detail. They got scuttled under political pressures, a lot of it coming from realtors. But you could throw a map out there and you might have such and such a position in your mind. Oh, it's my best guess that's a landslide. But for the property owner, that could be a 10-fold difference in the value of the property. So that's a scary thought. And again, I'm inventorying. One more before I ask my question. One more before I ask my question.
No.
All right, yeah.
Following up on that, I mean, how far away do you think we are from providing recommendations to decision makers like the city or the DOH, at least on a budgeting level, annual budgeting level, to mitigate risk or to at least hedge, our capital bets? It seems like every year we have another 3 or 4 slides that we're dealing with. I don't know if we should just, have a line item.
And you're all gonna have me map it, so.
Right, a reoccurring budget item that grows geometrically or something.
Well,
Right?
you better be in a bank account because some years you're not going to have hardly anything. And then you're going to have a year. Or, well, I would not like to see it happen, but what if there's an 18-inch rainfall here in 24 hours? You can't budget for that. You can't budget for that. I mean, it would be cataclysmic. So that's a great question, but I think this is where we're trying to let things evolve. But until you understand what the risk and the potential for occurrence, then that's good. It's only computer.
What's your bonus?
Yeah. I think it would be great to be able to do that, but it's a lot tougher nut to crack than flood. Because you know where the floods are going to be, and these are much less predictable. I mean, we often talk about thresholds in geomorphology. In river thresholds, the waters they're visible. Thresholds in geomorphology, like this PRT is shut down, right? It is no less safe today than it's been for the last 37 years in this season. It's less safe in January, February, and March in wet years. It's no less safe today than it was last week or anytime since that big slide. I can't tell you, when that threshold's going to go. And the straw that breaks the camel's back may be hard to detect. All right. Okay, that's great. And I love to talk to people, but no, Jim, I have to ask me questions. Oh, okay. How much is it going to cost to fix on board. Let me begin this by saying, no matter what solution I'm going to spit out here, I would never have done it where that rock came from. Or it would have been one of the last places I would have gone. I see a couple of heads nodding up and down, unexpected, but obvious places for the rock to come down, but that's not where it came from. And I do think there are things, but like we got this drape, somebody suggested shotcrete. These drapes are 1/2 as expensive as shotcrete. And also, shotcrete sometimes becomes your rock.
Yes.
Right. So this is about $25 a square foot. The largest scar out there is like about 3,500 square feet. So you do the math, we're not quite pushing up to $1 million for one landslide that would not have stopped the big one that came down. Right. And then I'm not an engineer, so this is way out. I used to be an estimator. That was my life before I went back to school after my hiatus, after my freshman year, which was well earned. This is the other thing that might be done, the geo rockfall protection barriers. Right? This is like their model of how good these things are at stopping. Right? And per linear foot in Austria, I found one website said about 7 million euros for a kilometer. Right? The roadway I looked at on Google Earth, I think I probably want to protect about 9/10 of a kilometer. Right, what's the euro conversion to dollars? 1.2. Yeah. So if you wanted to do this all along the Mon Boulevard, I mean,
Would that have stopped the 25-ton boulder?
no way. Now, what I hear, the drape though keeps the rock from getting away. It might have, if the drape might have kept it from bouncing so much, and it might not have, conceivably, it might not have made it to the road, or more likely, it would have snug up into the ditch. So there are mitigations. You can make it better, but total solution. This is fairly up to John Katara and the folks on civil environmental engineering. So thank you all so much for coming. Yeah. Have a look at this.
That's cool.